So our lecture today is on constrained optimization and Lagrange multipliers. So we need to figure out what do these words actually mean. So the first thing we want to figure out is what do we mean by constrained optimization? So we've seen before how to find maximum and minimum values of functions when they're functions of one or two variables. So in this case, we're going to be more interested in the two variable case. So if I have a function that looks like z is equal to f of xy, we saw how to find the critical points and then use the second derivative test to check whether we had a maximum or a minimum. But we really didn't put a lot of requirements on that. And in real world problems, it's often the case that we can't just plug in any x or y for our function, that there's constraints on the possible x and y's that will work. So let's think of an example of this. Suppose your grade on a calculus midterm depends on the number of hours you spend doing new problems per day, which we'll refer to as P, and the number of hours you spend reviewing your notes per day, which we'll refer to as N. And there's some function that determines your grade based on these two inputs. So we'll call that function f of Pn. Now, obviously we'd like to maximize the grade, so we'd like to find the maximum value of f here. The problem is we can't just plug in any possible values for P and N because there's limits on how many problems you can do per day, or how many hours you can spend doing problems, and how many hours you can spend reviewing your notes. So let's suppose since we have other obligations, maybe you can, the most you can spend, or the exact amount of time you can spend preparing for the calculus midterm is 4 hours per day. That you've set aside, you're going to spend 4 hours per day studying, no more, no less, exactly 4 hours. And so this means when we want to maximize this function f of Pn and figure out what value of P and what value of N give you the best possible grade, we have a constraint to that where we have P plus N has to be equal to 4 because we're going to spend exactly 4 hours. So what we want to be doing is figuring out the maximum value of fPn, but any P and N that we can consider for that has to satisfy P plus N equals 4. So this equation, P plus N equals 4, is called our constraint. And it's constraining the possible values for our inputs. So let's think about what these things look like, these constraints look like when we look at the graphs of these functions. This will help us visualize what's going on. So here's a typical, just a example of a function z is equal to f of xy, so this surface here in pink. And so obviously our absolute maximum value here is here up at the top. But what we're interested in is what if we have constrained values that we can have for x and y? So maybe we have some curve, g of xy equals c, and in this case we're looking at an ellipse in the xy plane. So the only values of x and y we're allowed to consider have to be on this curve. So in this case, on this ellipse. Any other x and y's won't work for our problem. So what this looks like is here's our function in pink, and then down here in the xy plane is this constraint that we're restricting. So the only values we're interested in on the pink are the ones that lie above this ellipse. So if we look at that, this blue curve here on the pink surface are the values of the function z is equal to f of xy for just those values of x and y on the ellipse. So when we're looking at this constrained set for what our x and y's can be, we can see this very top point here is no longer valid. We can't consider that. So instead our maximums look like they're maybe right here and right here. So we're only looking at what are the biggest and smallest values as we trace along this curve on the surface. So it's a totally different problem than just finding the absolute maximums and the absolute minimums, or even the local maximums and local minimums, because we have to only look at the values that are on this curve, so the ones that satisfy this constraint. So one way we can approach this problem is to look at level curves. So suppose we have some level curves here. So for our z is equal to f of xy, these are the level curves where z is equal to 2, 3, and 4. And now let's go ahead and suppose we draw our constraint. So the green line here is going to be my constraint, g of xy equals c. And so we can see this level curve here passes through my constraint at both of these points. But if I'm looking for the maximum value I can get out of f, Right? Like 4 is the biggest value we have graphed, but certainly there's some bigger ones up here that aren't graphed, and there's values between 2 and 4 of our f. And so if we're looking for the biggest possible f we can get, we want to know, and it satisfies the constraint, we want to figure out what is the biggest f that lies on this green line here. So obviously 2.9 is not it. We do hit 2.9 at both of those spots, but it looks like we're a little bit bigger than 2.9 at these spots in between those 2 points. So let's change our level curves a bit and graph some different level curves. Well, here's the explanation of what I just said. So now if we graph, instead of 2.9, if we graph 3, notice it looks like the constraint here just touches the level curve. So they're basically tangent at this point here. And so we hit this 3, but it doesn't look like we can move any bigger than 3 and still be hitting any level, or still hitting the constraint. Once we go past that, we can see, so even if we go to 3.1, notice the value where f is 3.1, our constraint never hits that. So we'll never have a point on our constraint where the function is 3.1. So this is too big. So we see the maximum occurs exactly where they're tangent, because once they're not tangent anymore, it'll either be too big or it'll be too small. So we want this point here that's on our constraint, but also where the constraint's tangent line is the same as the level curve's tangent line. So geometrically, that's what we're trying to find. So for this particular example, we can see what it looks like. So here is our surface, z is equal to f of xy. Here was my constraint here in the xy plane. And then I'm looking at this curve here above it. And I'm trying to figure out what's the biggest value. So it looks like it's right here, which looks like it's about 3, which is what it looked like from our level curves. So now let's figure out, how do we actually find those points? So we want the points where those tangent lines are the same. So here's saying what I just said is we want the tangent line to the constraint to have the same slope as the tangent line to the level curve. But the point also has to be on the constraint. So remember when we did the chain rule of multiple variables, we found that if we wanted to find, so we did this in that section, then we talked about it in the related rates and implicit differentiation section to get this part. So we saw if we wanted tangent lines to level curves or just curves g of xy equals c, the tangent, or the slope of the tangent line at any point, was negative the partial derivative of f with respect to x over the partial derivative of f with respect to y. So if you don't remember that, it's good to go back and review that. And so we want to find points x0, y0. So not only is it on the constraint, so it's on that green curve from the previous graph, we also want the slopes to be the same, which is the same as saying f sub x of x0, y0 over the partial with respect to y at x0, y0 is the same as the partial at x of g over the partial at y of g. Notice the slopes will be negatives of those, but we can cancel the negatives out. So we want to find points that satisfy this. So one thing to note here is that just in general, if I have two fractions being equal, those are equal if and only if the a is equal to some multiple of c and b is equal to the same multiple of d. So just think of like 1/2 is equal to 2/4 because I can scale the top and the bottom by 2. But if the scaling isn't the same, then they're not going to be equal. So when I take this fact, just basic fact about fractions, and I apply it up here to these equations with the partial derivatives, we get the following. So we want to find these points, x0, y0, that satisfy, well, the partial derivative of f with respect to x should be some non-zero scalar multiple of, with respect lambda times g of x, and then f sub y there should be a lambda here. It should be lambda g sub y. So they should both be the same scalar multiple, and then that point should be on the level curve as well. So be careful here. This is a typo. There should be a lambda here with the g of y. And then once we found those x0s and y0s, to find whether they're a maximum or a minimum, we either look at the graph, how we did above when we were looking at graphs, or we can look at values of fxy for points xy that are near x0, y0 to see whether, if it's a maximum, then all those f of xy should be less than or equal to f of x0, y0. And this lambda that we have above for the scalar, this is referred to as a Lagrange multiplier. So let's consider one example for this video, and obviously a lot more examples in the actual lecture. So let's find the maximum and minimum values of the function f of xy equals x plus y, but we're going to constrain our x and y's to be on the unit circle. So they have to satisfy x squared plus y squared equals 1. So this is a fairly simple example. So here our constraint function is g of xy is equal to x squared plus y squared, and then our value c would be 1. So we take these partial derivatives. These are all easy to take. So partial of f with respect to x is 1, partial of y with respect to y, or f with respect to y is 1, partial of g with respect to x is 2x, and partial of g with respect to y is 2y. And now we set up our equations. So we want to find where f sub x is equal to lambda g of x. That's where 1 is equal to lambda times 2x. And same thing with the partials with respect to y. So I get 1 is equal to lambda times 2y. And this is for some constant value lambda that's non-zero. So if we look at these two equations, the left-hand side for both of them is 1. So that means lambda times 2x is equal to lambda times 2y. And so since lambda is non-zero, I can divide both sides by 2 lambda, and I get that my point here has to satisfy x has to be equal to y. So we know any values that are going to give us maximums or minimums have to satisfy the condition x is equal to y. And now we're going to go ahead and use our constraint here for the x squared plus y squared has to be equal to 1. So if I use that with the information I just had that x has to be equal to y, we get x squared plus x squared has to be 1. Or if we add these two together, I get 2x squared is equal to 1. I divide by the 2 and I get x squared is equal to 1/2. So solving that for x, I get x is equal to plus or minus 1 over square root of 2. And then using the x has to be equal to y, we get our possible points that give maximums or minimums is 1 over square root of 2, comma 1 over square root of 2, and negative 1 over square root of 2, comma negative 1 over square root of 2. And then we can graph this if we like, and this will tell us which is which. So if I graph, the pink here is the plane x plus y, and then here, this is the blue is the values on that plane where x squared plus y squared is equal to 1. And then I've put the two black dots here. This is where we have x is equal to 1 over square root of 2, and y is 1 over square root of 2. And we see that is 2 over square root of 2, and that's our maximum value. And then if we look at x to be negative 1 over square root of 2 and y to be negative 1 over square root of 2, that gives me a value of negative 2 over square root of 2. And we see from the graph here, that's the minimum value, so the smallest value of z that's on this blue curve on the surface. So we'll see some applications of this in the actual class recording and see some more complicated examples. In particular, these Lagrange multipliers come up quite often in actual applications. They're particularly important in economics. They also come up in physics and other areas as well.